This is the first part of two-part videos over collisions. So we're in our momentum chapter, and we've been working up to this. Back in the beginning of the year, when we tossed the volleyball and we found the value for gravity for the free fall, the volleyball when it was in free fall, we had different accelerations at the beginning and the end. And I said, that's when your hand was in contact with the ball. So when we have two objects that are in contact and we're looking at the physics of those two objects, we're talking about collisions. So this is like a new can. We're opening up a new can here. And we have two kinds of collisions. We have what we're going to learn are inelastic collisions and elastic collisions. And we're going to start off with an inelastic collision first, and we're going to talk about what defines an inelastic versus an elastic collision. All right, so the first problem, we have a 10,000 kilogram railroad car labeled A, traveling at a speed of 24 meters per second, and it strikes an identical car at rest, labeled B, so it has the same mass. If the cars lock together as a result of the collision, what is their common speed just afterwards? So here we go, we've got A, and it's traveling this way at 24 meters per second, and it's going to hit B. So this is before. Let's make this direction positive. And afterwards, we're going to have A and B locked together. And we want to know their final velocity. Well, it turns out we can use conservation of momentum to solve for this. So we know that the initial momentum has to be equal to the final momentum. Well, my initial momentum for B is pretty easy. That's going to be 0. My initial momentum for A, remember momentum is mass times velocity, so I'm going to have 10,000 times 24. That has to equal my momentum and my final momentum. So I don't know what this final velocity is, but consider now that I have these two objects locked together. So I have to think about what's the mass going to be on the backside. Well, if this is 10,000 and this is 10,000, I'm going to have a mass of 20,000. And I want to solve for that final velocity. So when I do my algebra here and I take 10,000 times 24 divided by 20,000, I get a final velocity of 12 meters per second. 12 meters per second. So inelastic collision, for our purposes, when you look at a collision and the two objects stick together after the collision, so there's going to be two ways to identify an elastic collision. One is the objects stick together after the collision. Two objects sticking together after the collision. But the better way to define an inelastic collision is the kinetic energy is not conserved. Kinetic energy is not conserved. But for all collisions, whether they're inelastic or elastic, momentum is always conserved. Always conserved. Sometimes kinetic energy is conserved and sometimes it's not. So just to prove, let's see how much kinetic energy we lost. Now, where does it go? Because we know we have conservation of matter and energy, that energy cannot be created or destroyed. So where does it go? When we strike these two objects together, we have heat from friction. We have sound. We have maybe deformation of the metal, especially if it's a car crash where we have forces that, part of the energy is lost by deforming the shape of the metal. So that's where the kinetic energy is going to go. But we know that kinetic energy is 1/2 mv squared. 1/2 mv squared. And let's do the kinetic energy final is going to be the same. So here we're going to have 1/2, and our mass was 10,000. and our velocity was 24 meters per second. We're going to square that. My final is going to be 1/2. This was 20,000. And this is 12 squared. When I solve for the initial kinetic energy, I get 2.88 times 10 to the 6th joules. And for my final, I get 1.44 times 10 to the 6th joules. So if I take the difference between those, I get 1.44 times 10 to the 6th joules. And this was lost. So I have two things that tip me off that this is an inelastic collision. First of all, these guys stick together. Second of all, I lost kinetic energy, but the momentum is conserved. Always, 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 always. That's why conservation of momentum, especially in collisions, is very, very useful. You cannot assume energy is conserved in the bubble of mechanical energy. Now, it's conserved overall, but it doesn't stay inside of our mechanical bubble. It can leak out into thermal heat, friction, all those other good things. All right, let's take a look at this next one. Before we do, let me add some definitions in up here. So what about an elastic collision? So here's the problem with elastic. To be elastic, at least the objects have to bounce off of each other. Objects have to bounce off of each other. This is where you have to use caution, because you can have this scenario where they bounce off each other, but it's not elastic. So to determine if it's elastic, you have to look at kinetic energy. The most you can say when the objects bounce off of each other is, well, there really isn't. You can't use this. You have to calculate your kinetic energy. So a lot of times for our purposes, if we're looking at things bouncing off of each other, it's tempting to think, okay, that's got to be elastic. But an elastic collision is one where the kinetic energy is conserved. That's the definition of elastic. But the only reason I put this up here is we know if they stick together, it's definitely going to be inelastic. There's no way it can be elastic. But the big takeaways are, is kinetic energy conserved or is it not conserved? So let's look at one more sample problem. We have two balls and they roll towards each other. I'm going to go ahead and slide down here. The red ball has a mass of 5 kilograms and a speed of 4 meters per second just before impact. The green ball has a mass of 2.2 kilograms and a speed of 2 meters per second. After the head-on collision, the red ball continues forward with a speed of 2 meters per second. What was the speed of the green ball after the collision? Okay, so we have the red ball and it's bigger. And let's make to the right positive. So the red ball does not say, well, let's assume that our red ball, which is 0.5 kilograms, is going this way with a speed of 4 meters per second. And then I have a green ball here. And if it's doing a head-on collision, the green ball has to be traveling in this direction. And this has got 2 meters per second, 0.2 kilograms. So my incoming momentum for the red ball is going to be, let's look at our initial momentum. So my initials, P initial. I have 0.5 times 4. That's going to be positive 2. I have, what do we have here? Plus 0.2 times 0.2. And that is going to be negative 4, because 2 times 0.2 is 4, and it's in the negative direction. So again, this is where those signs really matter. So afterwards, it says the red ball continues forward. So this is before, and let's go to my final. P final, and here's my diagrams, right? I'm using diagrams. I have the red ball, which is 0.5, and it's now going forward at a 2 meter per second. And we want to know what's happening to the green ball. We don't know if the green ball is going this way or if the green ball is bouncing off and going this way. Take a second, pause the video, see if you can figure out what's going to happen just by common sense. All right, so I don't know. I know that this mass is 0.2, but I don't know what my final velocity is. So they want to know the speed of the green ball after the collision, and understanding if that's positive or negative is going to tell us the direction that it goes. I do know that this is going to be 0.5 times 2. So that's going in the positive direction. This is going to be positive 1. Well, conservation of momentum tells me that my initial has to equal my final. So if I plug these values in, I have positive 2 minus 4 equals positive 1 minus, plus some unknown value here, right? So when I solve for, this would actually be my momentum final of the green ball. So when I solve for this, and we're going to put this in as 0.2 VF. So when I solve for my final velocity, when I do the algebra, I end up with, I'm going to pause the video here. This should have been 0.4. I made a mistake here. This is 0.4. Sorry. Math error. So when I do my algebra, I end up with 1.6 equals 1 plus 2 v sub f. And when I solve for v sub f, I end up with positive 3 meters per second. So the green ball is moving this way with positive 3 meters per second. Did you get it right? Did you guess? Well, it kind of makes sense, right? Because if this is moving forward, this weighs so much more than this, and this was coming in with a pretty small velocity, that if we're looking at, we had a +2 momentum coming this way. We've got a very small momentum going this way. This ball is still continuing to go this way. It's a pretty good bet that this one had to reverse directions. But here's the next big question. Was the collision elastic? So now we have to look at the kinetic energy. So if I bring these values down, I have 1/2 0.5 4 squared. This is going to be plus 1/2 0.2 2 squared. Because I have my initial kinetic energy of this ball and the initial kinetic energy of this ball. Notice the signs went away. Energy is scalar. We do not look at positives and negatives with energy. So my initial kinetic energy is 4.4. My final kinetic energy, I'm going to have 1/2 0.5 2 squared plus 1/2 0.2 3 squared. And when I do my algebra, I found out that this is kinetic energy is final is 1.9 joules. So they bounce off of each other, but is it an elastic collision? Was kinetic energy conserved? Does my final equal my initial? No. Kinetic energy is not conserved. This is an inelastic collision. So that takes us back to the beginning where we said to determine if it's elastic or inelastic, you really have to look at whether or not kinetic energy is conserved. All right, we've got a series of sample problems. I'm going to go ahead and stop here, and we'll run this number 3 as our first sample problem on the next video. Okay, so part 2 coming up.